어, 아, 네. 알겠습니다. 네. 어, mm. Hi everyone. My name is Junsu Kim. I'm a graduate student in combined master and PhD program process. I'm very too happy to introduce my main continual learning concept for you guys. Today, I'm gonna talk about continual learning and continual learning concept and various tasks. So, okay, I'll begin with simple example for for easily explanation. Here's my today's roadmap. First, I explain why continual learning are very needed. And then I'll talk about forgetting and the main continual learning setting. After then, I will explain how continual learning is evaluated and introduce the main methods. Finally, I cover continual learning in vision task, introduce my papers, and share my future directions. Before I begin, let me show you what you can take away from this tutorial. Uh, I think if after the tutorial, I hope you can do these five things. First, understand why a model forgets. Second, understand how a control learning setting is defined. Third, have a simple way to read the control learning methods and papers. First, know what to check when evaluating the results. And finally, see how continual learning connects to visual tasks and various tasks. You don't need to remember all of things. Just focus on the parts that useful to you guys' personal domain. Okay, let's start with the two images on the slide. On the left, the model detects a bicycle, a car, a person, and a van. Next, the same model is trained to recognize a scooter. On the on the right, the new scooter appears in an orange bound box, but the old car bounded box has disappeared. This is the main problem in continual learning concept. The model learns something new, but it is lost some old knowledge. This is called catastrophe forgetting. Now let's see the same problem as a performance curve. Favor the updates. The blue score, this blue score stay high. After the update vertical line, the orange score goes up. At the same time, the blue score goes down. That drop in the blue score is catastrophic forgetting. Put simply, the model learns something new but loses a little old knowledge. Next, let's look at the usual way a model is trained and deployed. This slide shows one full cycle deployment from training a model to deploying it. First, one fixed data set is used for training, validation, and testing. After the model is tested, it is deployed. This is a very common machine learning workflow. This setup usually assumes the data will stay similar after deployment. But after deployment, the world keeps changing now. The blue example, sorry, the blue The blue example shows a changing in the inputs. Rain, different lighting, or a new sensor can change in what the model sees. And then the orange example shows a change in the target. Sorry. The meaning of the label may also change. These changes may look similar, but they lead to different control learning problems. So the first thing to check is what has changed. As new data arrives, the model needs to keep running. Otherwise, it may not recognize new ones. One simple situation is to combine the old and new data. Then the model can be trained again from scratch. Retraining from scratch may sound simple, but it creates four practical problems. First, the old data may no longer be available. Second, privacy or ownership may prevent us from using it again. Also, poor training needs more computing cost or more energy. Finally, retraining can cause deployment issue downtime. Continual learning researches how to update our model under these practical limits. This figure shows the basic continual learning cycle. First, we start the current model, then new data arrives. The model is updated under practical constraints. After the update, it is testing on both old and new knowledge. The updated model becomes the starting point for the next run. This cycle continues as more data arrives. To see why a model forgets, let's start with this simple figure. The blue points, these blue points form two groups from task A. The black lines, this line separates two groups. At this stage, this black line is boundary decision line. At this stage, the boundary works well, so task A has been very well learned. Then task B is added to the same model. The orange points appear in the upper right area here. The curved arrows show how task B pushes the model. But the same parameters also support the old black boundaries. Because of this, learning task B can disturb the solution for task A. This complex steering running is called interference, training interference. After the update, look at the black boundary lines. The blue points are still in the same place, but the boundary is now much flatter. The model changed because it ran task B. As a result, its prediction for task A can become worse. This is one way interference can lead to forgetting. Here we need to separate two terms. The orange box show complete during the update. This is interference. The blue box shows a later drop in order performance. This is forgetting, catastrophe forgetting. So interference happens during running timelines. Forgetting is the result we observed afterward. Okay. So this lines compares to extreme choices. On the left, freezing keeps the old score stable. However, the new scores vary improves. On the right, knife fine-tuning improves the new score, but the old scores goes down. Freezing blocks new running knowledge. Knife fine-tuning can diminish old knowledge. Okay, this figure shows the two goals of useful updates. Moving to right means keeping more old knowledge. This is stability. Moving upward in this way Moving over means learning more new knowledge. This is plasticity. Freezing gives us stability, but very little plasticity. Knife fine-tuning gives us plasticity, but it may lose stability. The goal is the upper right area here. The model should keep old knowledge and still learn something new knowledge. Okay. Before choosing something massive, we first need to define the problem. This slide shows 5 details to check. First, define what is changing. Next, check whether test data can be used. And check whether task boundaries are known. Then define what information is available during training and testing. Finally, define the goal and the available memory and computation cost. Once these details are clear, methods can be compared fairly. So with this setup in mind, let's look at the main continual learning setting. The first one is task incremental learning. In this setting, the model knows the task ID number or identify at test time. On the right, task ID 2, select head number 2. Head number 1 is masked, so only head 2 makes the final decision. This makes the problem easier, but the correct task ID must be available at test time. Okay, next domain is domain incremental learning. In this setting, the input condition is changing, but the answer space stays the same. The left image is dry, bright, and captured by sensor A. The right image is rainy, dark, and captured by sensor B. A car is still a car, and a pedestrian is still pedestrian. Also. Okay, the source setting is class incremental learning. Here, the answer space itself changes. In the image, the orange scooter is added beside the old blue classes as these images. The diagram on the right shows one shared classifier for the car, person, and scooter. There is no task identified at test time. So old and new classes compete in one shared model classifier. The stream setting tells what changes. The data stream tells how the data arrives. The top row shows task incremental learning, domain incremental learning, and class incremental learning. On the left, task boundaries are clear and the data can be revisited. On the right, it's simple is seen only once without clear task boundaries. These are separate choices. For example, class incremental learning can also be online and task-free. Now let's quick check the series setting. In case A, task ID 2, select head number 2. This is task incremental learning. In case B, the label stays the same. However, rain and dusk change the input. This is domain incremental learning. In case C, the scooter becomes a new classes. It joins the shared output space. This is class incremental learning. The title change defines the same. Okay, now that the setting is clear, okay, let's talk about evaluation and benchmark. In here, we can use 4 simple checks. First, record the performance before the incremental updates. Next, report the accuracy after each update. This shows how well the model handles all of classes seen so far. Then measure how much performance was lost on the old task. This is average bargaining. Finally, compare the old classes and new classes performance. Together, these checks show whether the model learns the new knowledge and kept the old knowledge. Performance so very important, but it is one of part of the result in continual learning. First, compare the main baseline. The base model shows the starting points. Now fine-tuning shows what happened without protection. Joint training give a strong upright reference. Then check the practical cost. Look at memory, compute, update time, model size, and access to all data availability. So many method may improve accuracy, but still be difficult to use. So always read the performance and the cost together in the continual learning research. Now let's look at some methods proposed to reduce forgetting or stability. These methods keep different kinds of information from the past. Some protects important parameters. Some keep copy to old model. Others stores real example or generate synthetic examples. More recent papers can also use a large pre-trained model. In other words, foundation models, large language models. These ones. Okay. So firstly, let's start with EWC. Full name is Overcoming Catastrophic Forgetting in Neural Network. EWC means elastic weight consolidation. It comes from, this idea is very simple. Some parameters are more important than other parameters. The blue area shows solutions that work well for task A. And then the orange area shows solution that works well for task B. After task A learning, the model starts from the blue points. If it learns task B freely, it may leave the blue area. Then it can forget task A. But freezing every parameter is also too restrictive. EWC protects the important parameters more strongly. It allows the other parameters to change more freely. This helps the model handle both tasks. And then next is LWF, name is learning without forgetting. This paper is that storing old images, example, LWF keeps the old model as a teacher, like distillation, teacher and student distillation. First, both models receive the same new images. Then the old model give an answer for the old classes. And then the current model learns the new labels. At the same time, it tries to keep its old answer close to the teacher's answer. Only the current model is updated. In this way, the teacher helps preserve old knowledge while training. However, the method depends on the quality of the teacher's answer. Another simple method is replay. Example is replay. Replay keeps a small number of old example in buffer memory. First, the blue example are taken from the old memory. Then they are mixed with the orange examples from the new data. The model learns from this mixed match. This let it practice all classes while learning a new class. Replay is simple and often effective. However, a smaller memory is a good example and require more memory, more computational cost. So I see ARL is a representative replay method. Its full name is incremental classifier and representation law. It uses a fixed memory of representative examples, old examples. These examples are called exemplar. First, old exemplar are mixed with new data. This updates the feature structure. Then the exemplar builds one representative feature for each class. At test time, a new image is matched to the closed class representative. So one memory suffers both running and prediction. However, each class gets fewer examples as more classes arrive. Okay. This example shows why the contents of the memory matters. Both buffer, both buffers have the same number of slots. However, the left buffer mostly constrains recent classes, like blue slots. However, because of this, part of the past is missing. The right buffer covers all four classes. It uses the same amount of memory. So a large buffer is not the only answer. The example inside the buffer also need to be selected carefully. Next is deep generative replay. This method is useful when real-world images cannot be stored. We can use memory buffer. It comes from the paper Continual learning with deep generative replay. This pooling. Instead of old images, example, the method keeps an old generator and the old server. First, the generator creates a synthetic old input. Then the server adds a target for that input. The synthetic pair is mixed with the new data. The new model learns from both. So the methods replace generate example instead of real exemplar. However, it depends on the quality of those generated exemplars. Okay, next, let's look at gem and hat. These two methods control how the model is updated. On the left is gem. Gem means gradient episodic memory. The orange updates would hurt the old example. So gem changes it to the safer blue direction, like, like this. On the right is hat. Hat means hold attention to the task. Hat gives each task a different mask. This limits with parts of the network can change. Gem needs memory. Hat needs task information and enough free capacity. We have now seen several methods for classification. Next, let's see how the control line problem changes when the output becomes more complex. In classification, the model predicts one class for an image. And then in detection, it must find several objects and their locations. In segmentation, it predicts a label for every pixel. Because the output is different, forgetting also appears in a different form. The model may lose an old class, miss an old object, or erase an old region. Okay, let's learn this extension with pure-shot class incremental learning. Pure-shot class incremental learning means new classes very few, we can access to very few shot amounts. Specify the model first learns similar base class. For these classes, it has enough training example. After that, each session has a new classes with only a few shot example, such as 5 or 10 images. The model must run the new classes from very little data. It must also keep all the old classes. So pure-shot class learning combines pure-shot learning and continual learning domain. Then let's look at the representative pure-shot class learning methods. name topic. It comes from the paper name Fuchsia Classic Learning. Topic represent the picture space as a graph. First, the old classes nodes are kept as stable anchors. Then a new node is added for the new classes. Only the nearby part of the graph is updated. The rest of the gray stays stable. So the idea is very simple graph neural network. Topic keeps the old structure stable. And then next, let's move on to object detection domain. The blue curve is still visible, but it has no label in the view train data. Only the orange scooter has a label annotation. During training, the call may be treated as a background. This gives the model the wrong signal. The model may forget the call even though it is still there. This is main challenge in continual learning object detection. So let's look at this problem one step. In the old task, the call has a correct label. In the new task, only the scooter has a label. If we use only the new annotation, the car becomes a background example. A continual learning methods try to recover some information about the car. That information comes from several places. It may come from the old detector, store buffer data, a generation images, or external model. The goal is simple to not teach the model that an old object has become background. Now let's see how incremental learning object detection handles this problem. Short name IELD. The first IELD keeps the old detector as a frozen teacher model. Then the teacher predicts the old classes score and old box location. At the same time, the current detector learns the new object annotation, class and location. It also tries to stay close to teacher predictions. So ILOD protects both class score and bounding box location. However, the teacher may miss some old objects. In that case, it cannot provide useful information about them. Okay, then let's briefly look at segmentation. The same missing label problem appears here. At the first step, the blue car region has a label. At the next step, only the new cyclist region has a label. The call now treated as background. After the update, the old call region may disappear like this. The output is a pixel map instead of box, but the main problem is the same, like object detection and object classification. The old content is still visible, but its label is missing. And then furthermore, recent continual learning methods can use a large pre-trained model, like large language model and foundation model. The pre-trained model can have in three ways. First, the large model itself can be continually updated. Second, it can stay frozen and provide useful features. Third, it can check labels or create extra information. It helps the continual learning model makes better updates. Now that we have covered the main continual learning methods, let me and then I'll talk about my own work. Across these papers, I explore different ways to preserve information from the past knowledge. I start with a real buffer memory in EVTS. Then I try to remove the buffer using generation model stable diffusion. Full name is SDDGR. After that, I used a visual language model to improve pseudo labels in continual learning for object detection. Next, I study when synthetic display actually helps. Finally, I move from generate images to the using features inside the diffusion model. Okay, I'll start with EVTS. In this work, I focus on using a small replay real example buffer more effectively. The method has two parts. First, it manages the memory classes by classes. This prevents recent data from pushing out the old classes. Then circular example replay use the store example one more time. Together, those two parts build a more balanced memory and use it more effectively in the object detection task. The selling point is better use of the same memory size. However, where all the images still need to be stored. This limitation motivate me to explore buffer-free replay or other tasks. So the next task is stable diffusion for with generative replay. In this work, I wanted to remove the old image buffer. Short name SDDGR means full name is stable diffusion based deep generative replay. It uses stable diffusion for continual learning, object detection, or removing old image buffer. First, stable diffusion creates scene with old classes. Then the refinement step in here, improves this scene. After that, the generate scenes are mixed with the new data and locations. Distillation and slow wavelengths also protect old object forgetting. So in here, the selling point is buffer free and no limitation for replaying synthetic images. However, continual object detection still depends on slow wave and stable diffusion. Improving those labs become the focus on my next work. Our next work is named Vision&Learning. This work focuses on the quality of improving the quality of store labels. Vision&Learning means vision language models based pseudo labeling. Specifically, first the old detector proposes possible old objects here. Then a frozen vision language model checks each region. It uses both the image and the class name. After that, unreliable boxes are removed. The accepted boxes become pseudo ground truths. Finally, the detector runs from the old and new labels together. The selling point is cleaner pseudo labeling through visual language model based correction. However, this method requires a large foundation model like visual language model. After this work, I wanted to study synthetic replay from a broader view. Next study for can static images conquer forgetting. Rather than focusing on another single method, this work study when static images actually helps in continual learning for classification. It focuses on three choices. First, quantity means synthetic image quantity means how many static images are used. Second, strategies. Strategies means how those images are made or selected. Third, timing. Timing means when they are added to whole training process. The results are very simple. Result is very simple. Synthetic replay does not always help in continual learning domain. If value depends on quantity, stretch, and timing. The selling point is practical guideline on when synthetic images for feature classing content learning. Okay, so this work let me to look beyond generate. Just generate simple images, and then I started looking at the knowledge inside the diffusion model representation itself. Okay, so final work name is diffusion feature classing content learning. Previously, I used diffusion mainly as a generator for generating synthetic images. In this work, I use diffusion model more broadly. Instead of using only generator, I also use the intermediate features inside the diffusion model, such as stable diffusion. The diffusion model stays frozen, and then text prompts are latent inputs produce several intermediate features in UNet architecture. Then small network combines like this. Small network combines those features for classification tasks. Only the small networks are updated in each session. The starting point is more flexible use of diffusion knowledge with lightweight updates. Across my papers, the source of past knowledge keeps changing. It starts with clear images. Then it moves to generate images and external synthetic knowledge. Finally, it reaches the intermediate features inside the diffusion model unit network. This progression leads to broader feature caching. Okay, before I wrap up, let me share my next research direction at a glance. You may already know Andrei Kafasi. At this March, he introduced a project called auto research. The idea is very simple. On large language model agents suggest change code or flat, then it runs a short experiment and checks the results. After that, it keeps the useful change and repeats this process. The human only focus on to define the goal. Goal means we define prediction score and the evaluation metric. I think this loop can also be used for continual learning and continual learning all of domains. The agent could choose what past information to use. It could also decide how to update the model. Then it could check both new running and forgetting strategies. This is promising direction. I want to explore next work, hopefully. Okay, let's wrap up. Summary. Today, I introduced one main problem in continual learning. A model should learn new knowledge without losing old knowledge. When you read a continual learning paper, first check what is changing, domain or task. Second, check what information from the past is available. Third, see how the method uses that information. Finally, check both the performance and the practical cost, like proper memory or computational cost. If you remember this four things, you can easily follow the main idea of recent continual learning papers. Thank you for your time and attention. Thank you.